Okay, hello everyone. Welcome to my presentation about the review about this paper, Code Translation with Compiler Representations. Actually, to fix my mistake in the notice in Google Groups, this paper is accepted. So the goal of this paper is to improve code translation using the intermediate representations of code in compiler. So my presentation outline looks like this. We see the introduction of the first session. I will introduce about the automatic code translation and related issues. Next, I will discuss about the intermediate representation in compiler. Then I will show you the objectives of this paper. Then we'll see the data compositions of this paper. Then we'll see the results of the experiment. I will discuss. Finally, I will conclude my presentation. First, an automatic translation. It allows to port old code bases to new frameworks, or we can say, in order to migrate programs or softwares which are written in old programming languages to the modern programming languages. We can call from the old programming languages such as COBOL, Python version 2. So in order to migrate to new programming language formats, we use automatic code translation. There are a lot of existing neural method translations, but they do have two main problems or limitations. The first one is unreliability. One code translation model can work on some programs. It cannot work with another programming language. And other unreliability issues are raised. The second problem is they do not understand the semantics of the input program accurately. So the intention of this program translation model is it uses the intermediate representation from compiler. Basically, in this paper, they use LLVM, low-level virtual machine, which incorporates about 30 programming languages intermediate representation. So IR is language independent representation of source code. So in order to make the naturalness of source code during translation, they prefer to augment the IR representation of every programming language which are considered in this paper. So we benefit a lot of things by IR, but in this paper setting, it helps us to align embeddings of different programming languages. It improves semantic understanding of the code. So in order to dive to the entire implementation of this model, let us see this motivational example. Basically, this example is comparing the baseline so-called transcoder and the current model, which is called transcoder IR. If anyone who is not familiar with the model transcoder, transcoder is a programming language translation or code translation, which is written by the same authors. The authors of these both models are from Facebook AI research, which is currently known as Meta AI. So transcoder was designed and developed in 2020. So it is translating between three languages: Java, Python, and C++. So if we see this example, on the first line is translating from C++ to Rust programming language. Here, there is misunderstanding or mismatch of the semantics of this input program with the translated one. Here we can see int data type is translated to useSize, totally different data types. useSize is it doesn't have any limitation like the integers 32, 64. So, but also C++ by default takes int data type as a signed data type. Here it translates as useSize means unsigned data type. So the transcoder IR, the current paper's model is fixed it in such a way. The second example is translating from Java to Go programming language. Here we can see the return term is totally mismatched from the input programming language. And also there are argument mismatches. So the transcoder IR have fixed it in this way. The same to that on the third programming translation. Here it takes this program to Go programming language. There is conversion with this shift operator. Here, if you see here in this line, the double greater than have confused with this single one. So the same here also, the parentheses have been closed early. So the second term here have been remained orphan. So the transcoder IR have fixed it in this way. In general, when we see these lines of codes, they look like simple and they can be fixed just by manual. But imagine when we code a program, even single line of code may make entire project failure. So that's we need the accurate and improved translation. If you don't have any question until this point, you are welcome. 질문 있으세요? Okay, I will continue. The contribution of this paper can be seen in this way. First, IR augmented translation have improved the translation averagely 5.5% improvement in all the programming languages considered in this translation, especially in the low data provision in Rust program. In this paper, the Rust programming have low data resource, so it has good improvement in translations. And also extended test in the baseline transcoder model. The authors have been prepared 852 test set functions. These functions are actually extracted from 4G's code documentation website. So functions are composed of C++, Java, and Python. So in this paper, 4 programming languages have been considered: Java, C++, Go, and Rust. So these authors have added 343 functions for Go programming language, as well as 280 for Rust programming language. And also, along with this code translation, the authors have also developed neural decompiler. It achieves 78% accuracy in order to decompile IRs to source code C++ program. In order to talk about the IR augmentation, we should have to talk about the compilers IR and related process. So in compiler, there are three components, main components. There are a lot of processes in compiler, but broadly we can categorize the compiler process in three: front end, middle end, and back end. And the front end side, indexing, parsing, and related issues have been carried out. So as AST also generated. From AST, we generate the IR representation. Here on the middle end, generate optimizations. Optimization tasks should have to be done. So after optimization, next optimization also expected, target architecture optimization. Finally, the output program, or we call it object program or binary code, or we can say it executable, will be yielded. So here for this code translation paper, the needed one, the required one is this one, generic optimized IR representation. Here, if you see these lines of codes, this minus O0 means just non-optimized IR. Minus OZ means optimized IR representations. So in code translation, we need the optimized one. Then we'll see how to implement, how to add this IR representation with source code tokens. If you do have a question until this point, you are welcome. Is there any question? Okay, I will continue. So why we are using IR? It facilitates this analysis and synthesis during translations. So we benefit to represent machine-independent code representation and optimizations. Programming languages which do have low resource in data training, we can benefit them, because IR is uniform representation of different programming languages. Currently, the LLVM, which is implemented for this paper, is incorporating around 30 programming languages. So when we see the objects of this paper, it uses unsupervised neural machine translation. So in unsupervised NMT, we should have to use these two main objectives. We should have to learn multilingual sequence embeddings, then align them. So the same functionality of different programming language tokens will be aligned on the same location when we visualize it. So in this case, we consider three variables: source sentence, its corresponding IR representation, as well as the target sentence. So in source sentence, we take code sequence of codes, code tokens. Here, the corresponding IR will be represented as ZX. So let me note these variables: Y for target, X for the code sequence, and ZX for its IR. So this paper uses the machine translation loss function. Here, there are three common objectives of unsupervised machine translation. These all objectives have been derived from the baseline model, by the way, from transcoder. Masked language model is BERT-like model. It uses it masks some amount of its data, then it reconstructs them. So it uses the cross entropy function to compute its target function. The denoising is just it takes some noises from the input sentence, then it computes the target function using machine translation loss function. The third one is back translation, generating noisy translation from input to target. Then it recovers or it translates back to the input. So the loss function will be computed using the machine translation loss function. In this paper, the special one is they add IR for additional information to make the code translation model strong and just robust model of code translation will be built using these three objectives. The first one is translation language model. Actually, this objective is taken from the paper so-called cross-lingual pre-training model, which is published in 2018. So it takes the sequence of X, the code sequences, then it augments their IR representation. Then it recovers the original tokens. Here, this sign is concatenation, actually. We will see in all these three objectives here, concatenation. It concatenates the original tokens with their IR representation. In the translation auto encoding TAE, it transposes TLM objective using the denoising autoencoder. So it takes the noised X sequences, then it augments or it concatenates with the noise IR representations, then it recovers the original augmented sequence. In the third objective, it is the same to compiler's process. It takes the source code, then it generates their IR representation. Here is an example. It is basically the first example is about TLM. It takes the source code and its corresponding IR representation. Here in TLM, we should have to note here, this is the complete representation of IR of the previous source code. This source code is corresponding with this IR. So TLM, its objective is it can attend both the source code as well as IR. For example, we can take here an example. The masked token here is the data type. So this model simply, it can look even the source code's unmasked token. For example, int. Here, the masked one is the function max. So the model can look both this source code sequence as well as IR sequence. So the next one is IR generation. It takes the source code, then the model generates it is so-called IR representation. There are also additional objectives, IR decompilation as well as IR pivot translation. IR decompilation is the reverse of compilation. It takes the IR representations, then it decompiles them, it reverses them to the source code. The second one is IR pivot translation. IR is used as bridge. It takes the uniform format of IR all programming languages. Then by taking one target programming language, then it can make translations. So it uses a neural decompiler for undertaking this process. Here is an example of decompilation. It takes C++ function. Then using the CLang compiler, we can generate the IR representation. Then using the MT model, we can decompile to its C++ source code. So here are the data compositions of this model. They use Google BigQuery for C++, Java, Rust, and Go functions. Google BigQuery is actually, it hosts the GitHub open source repositories. So for the decompilation, they use coordinate dataset. These are the composition, the amount of data used in this paper. So for generating IR representation, CLang for C++, JLang for Java, these all are used for respective programming languages to generate IR representation. During evaluation in this paper, they use a metric so-called computational accuracy. Computational accuracy is originally presented in the baseline model transcoder. For audiences who didn't know about the computational accuracy means we take the target programming language source codes or the translated source codes, and we prepare corresponding unit tests for every translation. If the translation is matched with the unit test, or if it passes the unit test, it is referred as good computational accuracy, or is the translation is good. If it fails that unit test, it's considered as failed code translation or low computational accuracy. It's just computational accuracy works in such a way. So as I told you in the contribution section, they add 280 for Rust programming and 343 functions for Go programming. So they evaluate in such a way. The experimental details can be seen in such a way. Here we can see they use the original transformer network. Actually, it considers 12 layers, 6 encoder and 6 decoder layers. They use also the same attention heads. 8 attention is the same with the original transform, which is present in the paper. All you need, attention all you need. But here the dimension is double. In the original paper, we know it is 512. Here it is 1024. 15% of tokens are masked for ML and TLM. 20% are masked for AE and TA objectives. Except MLM, all the objects are trained on function level. Actually, the transcoder, the baseline model is original. It is trained on function level. Only we can translate functions. These are the translation results. If we see these results, the objectives or the translations which have augment IR representation are dominating. The best result have been accommodated by augmenting those three objectives, TLM, TA, MT. If we see this result, the best result is using the IR augmented objectives. The authors also determine the beam search decoding beam size. Actually, is for determining their hyperparameter beam size. So they use beam size 10 and beam size 5. Here the beam size with 5 is dominating the result. Best result is recurred using beam size 5. When we see the decompilation results, Actually, their baseline is called RateDeck. RateDeck is machine code decompiler developed by Avast company. So actually, RateDeck decompiles C programming language, C++, and other programming languages. Here, they compare it with C++. This other programming languages do not consider in this baseline model. So they compare with C++, this model, the model which augments IR representation have dominated this result. So we can see here the same example with the previous we have seen in the motivational example. Here another issue is the bitwise operator. This one is already we have seen it, data type mismatch. And also here we can see this bitwise operator is a complement operator, or we can call it negation operator, not X. Not X is expressed in this way in Rust programming language. So when we see the baseline model, it translates it as it is, the same with the Java code. So the current model have fixed it in this way. The same to that, the data type here, it translated it the same way in the Java. Here, it have fixed it with the context of Rust programming language. The same to that here. Here we use the int type. Int is by default, it is unsigned, but the transcoder have translated as unsigned data type. Transcoder IR have fixed it in this way. The authors have also make some ranking of token similarities. Actually here, they take the ranking about the U32 data type of Rust programming language. They are ranking its similarity with the equivalent C++ data type. So if you see in the transcoder, it have the first ranked data type is U64, totally doesn't have any correspondence with this data type. So in this way, other embedding rankings also outperformed by this current model. Another issue with this demonstration is about Rust programming language data type errors. In the baseline transcoder, there are total 609 errors, data type mismatch errors. So the current model transcoder IR have minimized it to 463. So when we see overall the demonstration of this model, it considers C++, Java, Go, and Rust programming languages. These all are compiled programming languages. But the translation, code translation using IR do not limit it to compiled programming languages only. So interpreted programming language like Python can be also used using the IR representation. But here we should have to take an attention. The language pairs for translation should have the same IR representation. They should have to have uniform IR representation for translation. Another issue with this paper is about pivoting and embeddings. As we have seen on the previous slides, in order to make the code and IR aligned embeddings, we use this objectives TLM, TAE, and MT. The pivot translation uses IR level similarities between the uniformly represent IR print for all the considered programming languages. So these issues are main achievements of this paper. But when we see the prediction stage of this model, these three objects do not require during inference. TLM, TAE, and MIT objects do not require during testing. We take the input of any programming language source code, then we are required to yield translation on no need of adding IR during testing. So when we conclude the presentation, LLVM IR is good to improve the code translation. IR provides semantically rich language representation. Adding these three objectives, TLM, TAE, and MT, have yielded 5.5 average code translation improvements. The seq-to-seq transformer shows effectiveness on decompilation, as we have seen on the previous, decompilation section. So this approach can be extended to any pairs of programming languages for translation, but they should have to share common IR representation. So these authors have suggested that in future works, IR can be generated by compiling entire projects for solving parallel data limitation, which is a main problem for code translation, especially in this IR augmented translation. I have finished my presentation. If you have any question, you are welcome. Thank you.
So Gary, I raised my hand actually about 5 minutes ago.
Sorry.
No. So I have a question for the table 2.
Table 2. Okay. This one?
Yes. So what does that IR pivot mean in this table?
IR pivot means it takes the IR representation of all programming languages. Then using the IR similarity, it translates source code from one IR to the another programming language source code.
So to get the IR representation, so LLVM IR, you just compile the source code, right?
Yeah.
And then decompile the IR using the neural network here, right?
Yeah, it decompiles. Decompilation is another objective, but in the case of IR pivot, it uses the IR representation of all programming languages. Then it takes one program or one IR representation as source program or source sentence. Then it takes another programming language as target sentence. Then it makes translation. So the output is code translation, actual source code. The output is source code. For example, when we say from C++, we are taking as input a C++ IR representation, but the output is another programming language source code.
Yeah, so in the other settings, you only give the source code, right? In the high level language.
Yeah.
And
the
then
output,
directly translate to the target language.
Yeah.
And so in the IR pivot, you give the LLVM representation as well, right? In the input.
Yeah.
So, I mean, I think IR pivot should be better than the other settings because we basically give more information, right? So
yes, of course.
So weird.
But in this setting, there is so-called a problem, so-called IR dialect. IR dialect means the IR representation, which came from every programming language, have some dominance from the source program.
Really?
They say a program, an IR represent which came from C++, have some dominance, some slight difference from the other representation.
Okay.
The program came from Java, also same to that. Actually, for this purpose, these authors have achieved this result using decoder on the target program and back translation. But in general, IR private is very low efficiency in this setting, in this results.
Okay, so the name of the proposed model here in this paper is transcoder IR, right?
Yeah.
So the only difference from that baseline is the added objective functions, right?
Yeah.
And so the transcoder only use the MLM as the objective function to train the model.
Yeah, in the baseline model, we use only the code sequence. Nothing additional information is required. But
Okay,
this author's concern is actually before this paper, they have published also another, which is I have presented it in last year.
Okay, yeah, I remember.
Yeah, when they translate, they could not achieve the naturalness of language. In order to achieve naturalness of the translation, they use this IR because IR is close to all the source and target architectures. It can be, it is nice representation actually, but this the research on this representation is a little bit.
And one more question is, one more question is when you introduced about the data sets used in the paper, they collected additional set of functions written in Rust and Go, right?
Yeah, test sets.
But they don't have any parallel functions in the other languages.
Here?
Yeah, so only written in Rust and 343 functions in Go. There are no parallel implementations in other languages, right?
Yes, because here, a professor, they take the 852 parallel functions which are already extracted from GIGS4GIGS code documentation in transcoder model as it is. From there, they can be benefited for C++ and Java. As later languages, Rust and Go do not consider the transcoder model, so they add this test set.
Yeah, then how did they evaluate the performance on these languages? I mean, because there are no available pairs of these functions, right, in Rust and Go. So if you want to evaluate the performance of this model on Rust, then you have to have the pair of codes written in C and Rust, and so you try to translate the code in C to the code in Rust, right? And see functionally they are equivalent, but if there are no parallel functions like that, then how did they evaluate?
Okay, basically, if you see the test set of the transcoder 852, it's very few because they create unit tests per every of these 852 parallel functions. So these functions are parallel. For example, 852 functions in C++, 852 functions in Java, same to in Python. The same to that when they create tests in the Rust programming language and Go programming language, they create unit tests for every function. because computational accuracy means without unit test, either it is created manually or unit using automatic unit test generation, which is present on the previous paper of these authors. Unit test is mandatory for evaluating this model, because computational accuracy is based on the unit test.
Okay, so just using the unit test cases.
Yeah.
Okay, thank you. Thank you. 혹시 더 질문 없으신가요? 코드를 쓰는 대부분의 태스크에서 이 LLVM IR을 적용할 수 있을 것 같다는 생각이 들긴 하는데요. 네.
네?
So in this paper, they only consider code translation, right?
Yeah.
And they try to use this LLVM IR as additional input to this model to improve the performance. But I think for the other programming language related tasks, we can use this information, right?
Yes, of course.
In the same way. So
actually, there is one paper I have seen on yesterday.
So on which task?
It's called, it's not task, but it's evaluation. Evaluation is on code code repair, automatic code repair. Any interested person can refer fix eval. It's already focused. The evaluation should have to be effective on execution based metrics like computational accuracy. Even it disproves the code blue code evaluation metrics. So I think this IR representation also, it is execution based task, because the evaluation is whether the translated code is executable or not. So I think it is effective for other tasks also.
And can you share the title of the paper you just mentioned in this chatting room?
Okay.
Thank you. 예. 질문 있으시면은 예, 좀 해주시고 없으시면은 예, 곧 마무리하겠습니다. 걔네 그 채팅창에 질문이 하나 올라왔습니다.
오케이.
그 한 가지 좀 고려해 주셔야 되는 게 그
LLVM 세트에서
걔네 그 프로그래밍 언어를 주로 연구하시는 분이 아닌 분들도 계십니다. 그러니까 조금 더 간단하게 설명해 주면 좋을 것 같습니다.
LLVM 메테예요?
네네네.
LLVM은 한국말로 조금 해볼까요?
No, you can explain in English. They all I mean,
Okay.
yeah.
LLVM is a big project which focus on developing compilers, debuggers, and assemblers. So currently, it incorporates around 30 programming languages, IR representation. So its task or its activities are huge. They do have a lot of activities, as I told you. Developing compilers, debuggers, assemblers is very intensive task. But here we are using among the small parts of this project, which is IR representation. During compilation, decompilation, during assembly and executing program, they use IR representation in this framework. So we use IR for code translation in our current presentation. 혹시 이해하셨나요?
갑자기 참가시켜서 죄송하지만 그 수환학생 혹시 있으면 좀 설명해 줄 수 있을까요? 수환학생이 제일 잘할 것 같은데.
수학?
아, 네네.
네네네. 그 PLML 연구실 또 박사과정이신데요. 저기 또 계례보다 좀 더 오래 연구를 하셔가지고 좀 더 잘 설명해 줄 수 있을까요, 혹시?
아, 네, 한번 해보겠습니다.
네.
LLVM은 하나의 컴파일러라고 생각하셔도 되는데요. 보통 이제 특정 언어의 컴파일러를 사용하면 그 언어에서 이제 뭐 최적화를 한다든가 하면 그 컴파일러에 대한 최적화 알고리즘을 만들어 놔야 되는데, 이 LLVM을 사용하면 예를 들어서 C 언어에서 LLVM 컴파일러로 어떤 중간 언어를 만들어서 그 중간 언어에서 최적화를 하게 하면 그 중간 언어에서 최적화하는 거 하나만 있으면 뭐 C에서 LLVM IR로 만든다든지, 예를 들어서 파이썬에서 LLVM IR을 만들면 같은 알고리즘을 이용을 해서 최적화를 할 수 있죠. 그래서 이런 LLVM IR을 사용을 합니다.
네, 상세한 답변 감사합니다. 예, 혹시 더 질문 있으실까요? 네, 없으시면은 네, 오늘 이렇게 좋은 발표 준비해 주셔가지고 계례 학생 너무 감사드리고요. 예, 수환 학생도 갑자기 끌려 나와서 좋은 답변 감사합니다. 네, 그러면
감사합니다.
이번 주 세미나 여기서 마무리하고 다음 주에 또 뵙겠습니다. 예, 고생 많으셨습니다.